and how the data structures function and get us prepared so that in 2 weeks we'll be ready to go and work on some charting and graphing. So with that, I will turn things over to Chris.
Thanks, Keith. A couple things before we get started. One, I have a cold, so if I start coughing, I apologize in advance. I'll try to keep that to a minimum. Also, I did put up some of the stuff from our last time up on the GitHub page. So if you would like to see any of this stuff, you go to the website here. I have a copy or a link to the video that's been shared around too if you'd like to see it. I will have put the link up there again today, and then some of the material that we go over. If you would like to, before we get started, keep sending me feedback here. Go to the GitHub page. So this is GitHub, Chris Jasinski, OFWIM 2016, and you can see that there is this data directory. We're going to use this a little bit later. So if you can click on that, and oops, I grabbed the wrong one. So you can see the data.zip. If you click on that data.zip, it'll say, sorry about this, but we can't view it. You can click View Raw. It'll download it for you. And if you could take and extrapolate that into a directory that you will be able to use fairly easily, that will help us set up a little bit later. So I'll give everyone like a minute to go back through there. And if you have any questions on how to get there again, just let me know. I'll bring that back down. Sorry about that. Are you able to get that, Keith? So you'll be able to, any directory that you want that you have easy access to would be a good spot to put that. In that zip file, open it up here and show you. We have a couple different types of data. So we have some CSVs, some text files, some more CSVs, some R data sets, some SPSS, SAS, and Stata type data. So these are all different options that we will have to bring to when we load data in. Was everyone able to get it in? That wanted to get it in? Not absolutely necessary if you just want to watch as we go along here. Okay, I don't see anyone saying anything here, so I will get started and move on to R. So if we can open up R Studio, this is where we'll be working on stuff today. This is what we loaded and talked about last time. You can see when you open it up, click this in the upper left here and create a new R script.
I'm not seeing your screen.
You're not seeing my screen?
I'm not seeing your screen.
You see now? Hold on.
All right, now we're up.
Okay.
Now you're there. So.
Okay, everyone can see that now? Okay. So when you start up R Studio, click on this in the upper left here, this little notepad, and click on R script. You can see these are all the different types of files that R Studio can use. We're going to be working with R scripts. Kind of a good rule of thumb that I use whenever I'm working in R is that I create a comment, so that's what these number symbols are. Anything that you do after that is a comment, and it won't get read into R, and it won't try to do analysis. So what I always try to do is just put a title on the top so I know exactly what we're talking about, and then the date that I most recently worked on that. That's very helpful when you come back and try to look at your script so you know exactly when you were last working on it. Now, we talked last time that R is an object-oriented programming language. So what we often do is create objects. And there's several different objects and data structures that we can just type it into the console like we showed last time. 2 plus 2. You hit enter. That's just like a calculator. You get 4. We can also assign those variables, those numbers, to an object. So we can create an object A and assign it 2. So we now can then go, if we click, you can highlight this and then run that. We now know, you can see down in the console that A is 2. If we click on A, write A down there in the console, you can see it spits out 2. So 2 has been stored in the object A. You can also make one B is 3. We can run that, and we can get A plus B is 5. So we can store data in these objects, and then we can run functions on these different types of objects. And there's several different data structures that we can use in R. If you're really interested in some more of this stuff, there's a really good book out there. It's called Advanced R. So there's a lot of it here, but they have a website. Hadley Wickham has it, and it talks about all the different data structures in a lot more detail than we'll actually go through today. But there's some good information. There's some quizzes that kind of help you test your knowledge on things. It's a good website for some of this information. So and I'll provide that link. I'm going to provide all this information for you guys later. So the basic form of data is assigning this to the objects here. But we can also use vectors. So the vectors have certain properties. Vectors are a sequence of numbers, characters, factors, and strings. One of the important things is that in the sequence, all values must be the same. So you can't necessarily in a vector have a number, a character, and a factor. They all need to be the same thing within that structure. The other characteristic of a vector is that it is one-dimensional. So to create a vector, we can use A again. So we'll overwrite our object A, and you use this C parentheses. And this C means combine. So anything within this parentheses becomes that vector. So as an example, we can go 1, 2, 3, 4, and 5. And when we click Run, we now have assigned those numbers into A. So if we write A now down at the bottom, you can see that it's 1, 2, 3, 4, and 5. I guess one thing to note, too, for people that are new to R, you can see that this arrow is essentially taking and assigning whatever you have on the right side to the object on the left. You can also, if you really dislike the arrow, to use an equal symbol. So it does the same exact thing, but kind of a R tradition to use the arrow. So that's what I tend to use. It gives us the same thing here. So there's a couple things that we can kind of explore and identify what type of our data structure we are working with. So one is the type of function. So we can go type of A. And if we run that is a built-in function. So we're taking this, everything within the parentheses is what we're trying to identify. You run that, and you can see that this is type of double. And double is just that it is a numeric value. That there are no singulars in R, only doubles. So that's representing a number there. We can also look at the class of A. So that tells us that this is a numeric value. A couple other things you can do to kind of look at the structure of the data. So dim is a way to look at the dimensions. So the dimensions of A, if we run this, you get a null down here at the bottom. And that is R's way of saying that it doesn't have a dimension. So because we are working with a vector here, it is one-dimensional. It doesn't have a dimension essentially.
Hey, Chris.
Yes.
Can you share the URL for the data downloads again?
Oh, sure. Let me just pull it back up. Actually, I'll paste it in the chat. So here, if you go to GitHub/ChrisDaVinci/OFWIM 2016, here is the GitHub page, and the data zip right here is the file you want to download. Click on this. It'll say that it can't find it. That's because it's a zip file. That's fine. But if you it'll download it for you. So, or you can hit download here. But if you just click on that, it downloads it.
Can you copy and paste that into the chat?
Sure.
I'll do that. I got it.
You got it?
I got it.
Keith will get it for you. Okay, so yeah, we were talking about the dimensions of A. It's one-dimensional. It's going to spit up a null, so that R's way of saying that it doesn't have a dimension. But if we want to know the number of elements in that vector, we can use the function length. And length tells us how many elements are in there. So we run that. We see that there are 5 elements in there. There's a couple other things that we can try to do, very similar to dim. A couple other common functions are nrow. That, very similar to dim, is the number of rows. That will spit back and tell us null again because it is only one dimension. So there's nrow, and then, as you might guess, there is an ncol, which is the number of columns. You can run that. Like I said, there is no dimensions there, so that will spit up null. But when we start looking at some of the multi-dimensional data structures, we can use those things to explore that data. A good practice to get into when you are working in R and looking at some of the data structures, and you want to just kind of look and see what they are, is to use this function str, which is the structure, and you just provide it the object. And depending on what it is, so this one tells you that it's numeric, that it has 1 to 5 values, and then it will display the first few values in that object. So this really good practice, whether you're bringing data in, whether you're creating your own data, it's always good to take a look at that data and get a good idea of what it looks like, what values, if it's numeric, if it's reading it in as characters, there can be all sorts of issues that pop up there. So it's really good to explore this stuff and make sure it's in the proper structure that you want it to. So now that we've created this object, we've looked at it a little bit, we can then apply some other functions to it. A lot of the statistical functions are built, R likes to be vectorized, so it will run its functions across vectors. So as an example, we can run sum, which would sum everything in that vector. You run that, tells you that it's 15. And a lot of the basic statistical stuff, so you can do mean of A, you can do standard deviation of A. We run these two things, and you can see the results. We can also start stringing together several of our functions. So to do the standard error of that vector, we could go standard deviation of A divided by the square root of the number in that vector. So we can run this all, and it pops up the results down there. The other nice thing is that we can also take this string of functions and store this as a value. So you can go standard error A is equal to the sequence. So we can run that. We now have stored our standard error in this object, SEA. And this can be done with a lot of different data. You can store all sorts of data structures in objects. We'll kind of talk about more and more, some more of the data structures that are a little more forgiving on what kind of data. There's numerous kinds of classes in type of data. So in R, so numeric, we just covered that. Numeric is just numbers, and that is the type of double. There are characters. So we can also create a vector of characters. So you need to use that C. This is a big hang-up a lot of times, that people try to create objects and they forget that C in there, that combine function that's telling R to group all of those things in a vector. So if you see an error, a lot of times you're forgetting that C. So characters need to be in quotes. Separated by commas. So if we run this and we take a look at B now, you can see, and it'll display the quotes around that down at the bottom. So a couple things about characters in R and object names in R. So capitalization is important in R. It does in A, so let's so capital A is a different object than lowercase a. So you can see they're two different objects. So the same thing goes in under our character values, that capital D is different than lowercase d. A common thing that also happens in this is white space is important. So if you had a space here, that is going to get passed through. So if you look at this now, you can see down here, we do have a white space in there. And so if we were to run A equals D, we can see that we're getting a false there because it is not recognizing this D as the same as this D. So that's something really important. And when we talk about importing data in, that is something that you'll really notice, that there are some functions that are better not about stripping white space off there, because especially when you're bringing things in from Excel or other spreadsheets, it can cause all sorts of problems. So another type of data or class of data in R is factors. And factors are very similar to characters, except for they have a level to them, that they're ordered. So if we look back at B, again, we have A, B, C, D. So a factor, we can create one C, actually we'll call it D, is a factor. We will supply it B, and then we can supply the levels in there. So let's make these go in opposite order. So D will have level 1, C, B, and A. By default, if we did not provide those levels in there, R by default would put the levels in alphabetical order. So it doesn't matter on if it's a string, multiple characters all together, it will do them alphabetically. If we run this now, we just created an object D that is a factor of these levels, or these characters with these levels as opposites. So if we now write D, we can see that here's the data, and here are the levels. So D gets a value of 1, C gets a value of 2, B gets a value of 3, and A gets a value of 4. So this is important because a lot of times in by default, in a lot of the programs, there is the strings as factors. And a lot of times when you bring data in, it will automatically convert those to a factor. So depending on how you're analyzing your data and what kind of manipulations you're doing to it, it can end up giving you very different results than you would expect. So it's important to understand the differences between the characters and the factors. So we can also look, so printing off D here, we see that it gave us the values and the levels. We also can just pull up specifically the levels. So you can run levels D, and that tells you the order that those levels, or the factors are in. So the nice thing now is that we can also start converting between our different values. So if we go back A, run that. So we run class A. We see that it's numeric. We can convert A, we'll call it A.C, and we can go as character. And we provided A. So we just converted that 1, 2, 3, 4, 5 to character values. And if you go to class now A.C, run that, you can see that it's a character value. We also have the ability to change it to a factor. So as factor A. So if we look at A.F now, we can see that here are the values and here are the levels associated with each of those factors. And we look at class. We can see that it is now a factor. So there are a couple things. You cannot convert a character. So where do we have our characters? B. So B we'll call it B numeric. So if we try to convert B, which remember B was our character value, A, B, C, D, as numeric, it's going to say NA is introduced by coercion. So that means that in this vector, there was nowhere that it can take an A, B, C, or D and convert it to a numeric value. So you can't go from character to numeric. You can go back to D. Remember, D was our factors. If we convert D dot just D. So now if we look at D dot N, you can see that the values were converted to numeric, and that's based off of the values or the levels that it was in. So if we go back to look at what D was, It was A, B, C, D with levels D, C, B, A. So A got converted to a 4, B a 3, C a 2, and D a 1. So you can convert between those different things. Like I said, you can't convert characters to numeric. That's about the only one thing. It is really important, like I said at the beginning, to make sure that you're understanding and looking at the structure of your data to make sure it is in the appropriate class. Because this is an object-oriented language, depending on the class means that functions will treat it differently. So it's pretty important to know that stuff. There are a couple logic functions that you could run just to be on the safe side to test. So you can go is numeric on B. We run that. That will spit us back. I went to A. So that was the numeric vector. 1, 2, 3, 4, 5. Is numeric. It gave us a true. So in our logic, true logic would be true. It's all capital true or all capital false. B, remember B was our character vector. This will spit back a false for us. There is dot character. We can run that on B, and that gives us a true. We also have another function, is dot factor. If we run that on D, you'll see that that is true. So that's a good way, if you need to just run one of these on your data set if you're not sure how it's behaving. The other way is to use that str, which will tell you what the data type is. So as an example, str factor with 4 levels. Here's the values, and here's the numeric levels. Any questions on any of those basic data classes or vectors? So vectors are kind of the base of what we build up from here on out. The next type are matrices. And matrices are very similar to vectors, except for that they are two-dimensional. So one, it still needs to be and this is primarily limited to characters and numbers. The difference now is that this is two-dimensional. So to create these things, we can, so we'll create an object a.m. This is matrix. And the way that you specify this is that you want just a single value in there, you place that first. Then you specify the number of rows and the number of columns. So if we run this now, and we take a look at AM, you can see now we have a matrix. Here are the row numbers, here are the column numbers, and there are zeros in all of those. So now we can run dim on a.m. And we can see here are the rows and then the number of columns. We can also run nrow again, a.m, and ncol now. And that would spit it out individually. So the one thing you always need to remember here when we talk about indices and moving around data is that it's always rows by columns. So when you're specifying when you want to work with a certain row or a certain column, you always go with rows first and then columns. If we wanted to add some other data besides just zeros here, copy. we can specify a sequence. Here's 1 through 20. So this, by putting a colon between two numbers, means that it would move in increments of 1. We run this. You can see it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So that goes by column is the default. You can also have it specified by row, by saying by row equals true. And we can run it that way. And it would then generate them across rows. So, as I mentioned, all the data needs to be of the same type. So suppose we had a sequence that we wanted to add in here. Where it is a sequence, or C in here, 1 through 19, but then we have a character at the end. And if we look at this, try to run it, it runs, it doesn't give us anymore. This is another area that problems can arise. If you mistakenly have a character or a blank space, it will often convert all of your numbers to characters. So you would need to go through and either remove that character or change it to an NA, which we'll go over here in a second, to get those all changed back to numerics. And by default, it always goes, if there's a character involved, everything is converted to character. So there are a couple different types of data that still would you allow. Missing data in R is NA, capital NA. This would allow this to stay as a character, or as numeric, I mean. So there's a lot of other programs. I think SAS uses -999, I think, as missing data. Each program kind of does something a little bit different, but yes, R is capital NA. So we run this now. You can see that this still remains the numeric values, and now we have a missing value in there. There's a couple other types of data that you can have in there. So we can have an infinite. If you run that, you can see that this still retained numeric values, but this 4 by 5 is an infinite value. We also have, that was positive infinite, you can have negative infinite. Does the same thing. And the last type is not a number, and that is specified as NaN. So if you try to divide 0 by 0, you'll get not a number as popping up in there. And then we can also apply some of these same sort of values here, run the same sort of functions on there. So we go back to our AM3. We can run some on AM3. A.M. So if you run that, that sums all of your elements together. If you wanted just row sums, there is a default function in there. Go A.M3. That would give you your row sums. So that gives you that. And there's row means, col means, a couple other different statistics ones. But if you wanted to try to run another function, there is the kind of the powerhouse in R is to run apply. In apply, you specify the data, so A M3. You provide it the direction that you want. So 1 would be row, 2 would be column. So we go to column, and then you provide it the function. So we wanted to find the maximum value in each of those. We can run it that way. So if you go back and look at AM3, you can see that 17, 18, 19, 20 were the column maximums there. This is a pretty helpful function because you can provide it in any direction, but you can also work with individual elements in a cell. So if you needed to convert actually, we'll stay here. So you can also apply them to individual elements. So if you wanted to have a matrix that was the log of those, you would provide 1 and 2. So that means every single element in there. And you could provide log. If we to run this, it applies that log function on every single element there in the cell. So it's a pretty handy function. I use it quite frequently in editing and manipulating different elements in the cell. Okay, so that's matrices. So the next level up from matrices are data frames. And data frames are the thing that you will most likely use all the time, data frames. And the difference between data frames and matrices is that you are allowed to have different types of data among columns. So it needs to still be all the same data frame within a column, but you can have differences among columns. So as an example here, we'll create a new A. A is data frame, and we can have first col is equal to 1 to 10. We can go second col is equal to letters, 10. And we can have third col is equal to letters 1 through 10. And we can have those be a factor. So we run that, say A. We have first col, second col, third col. We actually have all 3 different types of data in here, or classes of data. And if we run str on A, you can see now that we see the structure. Overall, it's a data frame with 10 observations of 3 variables. First column is an integer. Here's the values. Second column is character with those values. The third column is a factor with 10 levels, and here are the values. So, like I said, data frames are going to be the thing that you work with most often. Anytime you input data, it should come in as a data frame. It is definitely the easiest ones to use. One other thing that helps when you look at with data frames is the head function. So head of A will display by default the first 6 rows of that. So I almost always do this to make sure that everything's been brought in correctly when I'm loading a data set. There's also the opposite, tail A, which will display the bottom 6 rows of that data set. So those are str, head, and tail are probably some of the most useful functions when bringing data in. Just a couple quick things on indexing. We can get moving into some of the data inputs here. So to display certain rows and columns, you use the bracket, and then you supply the row in the column that you want to look at. So going back to our, let me fix this here. So looking back at A, if we wanted to look at the second column, first row, we provide it 1, 2. And we run this, it'll bring up that element in that cell. If we want all rows in the second column, we have a couple different options. You can just provide it a comma and then 2. Or you can actually specify if it has a column name. This one was second column. You can also use a $sign, and then that you can see as you use this in RStudio, brings up the different column names here. So you can say a third column and run that would bring up all the elements in that third column. So there's a couple different ways you can select and choose different cells. You can also combine this. So if you wanted the 5th element in there, or the 5th through 6th, you can say 5th through 6th, and that'll display those values there. Choose more elements. Say you wanted the 1st, 3rd, and 5th element, you would then use your vector here and do 1, 3, and 5. So that tells you what those are, and then here are all the elements, or all the levels of those factors. One thing to know, if you try to use length on A, which is a data frame, it will not give you the number of rows or which most people think, it's going to give you the number of columns. So that is always something you have to be careful of. Get really used to using length. A lot of times, just doing that will give you the wrong information. Any quick questions on any of this? I have a few more notes that I can give and have people download and look at here. I'll put those up on the GitHub page. So if you wanted to explore a little bit more, so I talk a little more about how to select different rows or choose ones that drop rows or select different columns. So there's a little bit more information there. But I'd like you to move on to kind of, I term it the Wild West of data structures. These are lists. And lists are pretty much free to do however you want it. So we can have list, specify that list. So we can now have list, specify 1, and we can have this first one being a vector. We can have the other part being numeric. And then we can have the third part even containing a data frame. We run all of these. We look at our list. You can see that it's flexible. It doesn't. We can have different kinds of data. We can have different lengths of data. We can have nested loops or nested data frames within there. It's a pretty flexible format. If we look at structure on that, you can see it's a list of 3 items. First one's character, next one is numeric, and then the third is the data frame within the in the description of the elements within there. So lists, generally I don't ever use lists. The one thing that I use them for is when I'm running simulations or loops. It's a good way to store data or to output a whole bunch of different types of data because it's not required to have the same number of rows and columns or the same sort of data types. It's pretty flexible to store data, and that's how we used to store a lot of our Creel analysis was all stored in loops where we had nested data frames within nested data frames, and it can get pretty complicated. Generally, I try to avoid them, though, outside of data storage. It's difficult to run analysis on those. There are some functions, some different applied functions that you can use on lists, but they're fairly complicated. So I try to use it just for data storage, and then I can bring it out and do analysis across, or store results in there, not necessarily even data. Any questions on any of the data types? See any? Okay. So let's talk about inputting some of the data. So there's been some recent advances. I mentioned this last time, that a lot of the stuff that we do in R can get complicated, and some of the base functions that we have in R are not necessarily user-friendly, and that things can get pretty hairy when you're trying to manipulate columns or reshape your data from wide to long formats. They were not great functions to begin with. But recently, Hadley Wickham, who does ggplot and a lot of these other functions, has come up with this kind of grammar of data, and it kind of goes with his new book, R for Data Science. It is currently in development, but if you want to go look at it, it's all on the web. You can look at it, and it follows this tidy tools manifesto about how data should be structured, how you should manipulate it, all sorts of things, how functions should look, and that it's user-friendly. And he has put together a lot of functions that he has created that follow all the same sort of philosophy on how functions and data should be used. And one of them is this reader function, and then there's tidyr, which we'll get into at the seminar, and dplyr. These are extremely helpful functions. But today, this reader is really helpful for importing different types of data files. So I'll show you how to. So you can install this package by going install packages and then parentheses and put in quotes, and you can put tidyverse packages, tidyverse. If you run this, it'll go to the CRAN website, like I mentioned before, and it will download all the files for you here. And the nice thing is that there are, within tidyverse, there are lots of different libraries. So rather than trying to go and load and install every single one, we can just install them all combined together and install packages. The other nice thing is when we load this library, tidyverse, it loads all of the main ones that are there. So this Tibble, which is a type of data, tidyr, readr, per, dplyr, and then it tells you any sort of conflicts that some of these packages with names might have. So filter and lag coming in dplyr, they have a conflict in name with that. So it tells you that if you try to use filter, it's going to use tidy. Like a dplyr version, not that. This is a good thing to work with. We will be going more in depth with this at the seminar, as I mentioned, in a couple weeks. Okay, so let's work at getting some of that data. So there is an internal type of data in R, and this is called an .r data format. So as an example, there are some internal data sets we can take a look at here. And to load those, you just use data and iris. This is a common data set that's used to kind of explore how different functions work, different ways that you can analyze things. So if you put data iris, you can see that Let me sweep this and clean this up first. Try that again. So you can see that it shows up in the global environment. Iris shows on it. That means we haven't actually called upon it yet. So we can now run head iris. And as soon as we run that there, you can see that it's no longer promised. It's brought into the environment. Species of it. It has 150 observations of 5 rows. So if we wanted to create a new data set out of this, so say we were working with this and we wanted to save it as something different, we can say iris new, and we're going to save it iris. So we're taking iris, we're saving it as a new object iris. So to save this as in its internal format, we just use save. We provided the object we want to save, so that's iris new, and then we need to provide it our file location. So we do file, and you provide it the path. So as an example, OFWIM data. And we put it in the data folder here. You then provided the name, so this is iris new dot r data. And then we can run this. And see here in that directory, I have this iris new here. We just saved it. So we can now, we wanted to remove our original iris there, or remove that item from our environment. You can see here in our global environment, we have iris and iris new. We want to remove those objects, so we wipe everything clean. We go iris, iris new. We run that. We now have an empty environment. So we've removed those objects. Now, we just created this iris new.r data set. To load that data back in, we just provided the file, or the path and the file name that we just created. So now when we run this, you can see it automatically is brought into our global environment. We now have iris new in there. There's a couple things about the R data format. If you try to just double click on it and look at it, see if I can try to open Notepad here. There's one. So you can see that you can't just necessarily go and look at the data, unlike some of the CSVs and tab-separated values. You do need to bring it in, load it into your environment before you can see actually what the data looks like. I don't know if necessarily there's one benefit or not of using our data. It's just their internal format. I tend to use other formats over the R data. One of the nice things is that you can, say you're doing a lot of work and you've created lots of different objects and you suddenly need to leave your computer, you can save everything all at once in your environment with save image. And then you would just provide it the path to where you wanted to go. And that would save everything here. And then so next time you can do load and provide it this path, and everything will get brought into your environment and history and all of those kinds of things. So I tend to not use that either very much, but that is an option. One thing to note, though, and this causes lots of problems that I've noticed with grad students and stuff, is if you go to global options in your RStudio, this is by default on there. So what it will do is automatically save your image on when you exit RStudio, and then it will automatically reload that back up. So if you've made an error in some sort of in an object or something was not calculated correctly, it will automatically, no matter how many times you restart, you just get in this loop that it automatically reloads that data. So I tend to always make sure that that's checked off, and then I have save workspace to rdata on exit as never. You have always, never, or ask. These two things I think are really important, that you're not bringing in errors or anything like that by accident. How do I get rid of this?
Hold the options window down.
Hold on, I couldn't get rid of that there. So that's the Rs internal. Like I said, that's not, most often you're not going to be working with that kind of data. Most frequently, you're going to be working with either tab separated values or comma separated values, and that's where that reader package comes in. There is an internal way to read CSVs and TSVs, but the read underscore CSV, which is in that reader package, has a lot of good things in it. So to pull that up here, we can go look at the help of read.csv. So you look at the help file here. Here's the descriptions of them, and here are all the internals that you can, or all the specifications and parameters that you can have. And one of the nice things, as I mentioned before, is that there's this here, and you can have the white space trimmed off values when you input it. And so, as I mentioned before, a lot of times, whether you're having people enter data that don't really know what they're doing, or they accidentally fat finger and hit a space bar while they're entering a number, that can be read in as a character, and then everything you know, or everything that you have just brought in comes in as a character, and you have to go and track it all down to see what's going on. If you have this trim white space on there, it will automatically check that off, which is very, very, very helpful. Otherwise, it's pretty similar. It is, because this is comma separated values, it's going to automatically look for commas to separate the columns. If for some reason you have a European data set, which doesn't use commas, it uses semicolons. So to do that, you would use read CSV too. But generally, the data we worked with here that coming from Excel is comma separated. So to show you how this works, so if you've got that data downloaded, there's a couple things here that are a little bit different than what we just did with the load in the R internal format. And in this one, you're going to provide it the name of the function and then the path to that data, and then you need to save it as an object. Before, when we used load, it was already an R object in there, so it was automatically brought in. Now when we use read CSV, we need to specify what object we're saving it as. I'll show you here as an example. This is my path that I have here, so you might have something a little bit different there. So we run that. You can see with this read CSV, it kind of gives you a little information on what it did. It tells you how it created it. So site was brought in as a character, quadrant number was brought in as an integer, total mass was brought in as double, and then furrows was. It's a little bit different. The default way to read in data in the CSV data with base R is read.csv. So it's very easy to get confused between those two, but I really push people to use this read underscore rather than the base one. It definitely not only just that white space, but it tends to work a lot better. You don't get columns of NAs and rows of NAs that you often do with this read.csv. So another thing to look at here, when we run land crabs now, because we're using this package in the tidyverse, we now have a tibble. And I don't know where the name came from. It is kind of a dumb name, but this is the standard format, the clean data format that Hadley has come up with to work across all his tidyverse. So the first one is cite. It tells you characters, one, numbers, integers, total mass, double, numeric values that are not rows, and then it tells you the number of rows. You can convert to a table and a data. So if you really hated that, and create a new object data frame that is as.dataframe. That you can do the same thing with matrices and data frames. So run this now. So in the native data frame type, you can see it looks a little different. It doesn't tell you that it's a tibble, doesn't give you a display of the rows and columns, doesn't provide a description of the characters. You can still do all the same sort of analysis with these two, but the tibble provides a little bit more information of what your data is than the native data frame format. So then we also have the read TSV. So those are tab-separated values. And this works a lot better than the read.table in BaseR. I just had a graduate student come up yesterday that was trying to read in a tab-separated value data set. And for some reason, it was concatenating every single item into one column for just some of the rows. And he could not figure out what was going on there. He could not find any sort of error, but he automatically tried, or he went and tried the read TSV. It loaded with no problem. So it is also a little bit better than the one in BaseR. So it's a very similar approach here. So we provide in this data land crabs you do have in that data set that I said. It should be the green CSV, and then this text one is the green underscore text. Those both should be in the data sets that you downloaded today. So very similar to our read CSVs, we have the read TSV now, and we provided the path. We need to make sure that we provided the object that we're going to save it as. So if we wanted to, we could call this one tab. We run that. Very similar to what we just had in here. One thing to note, that this one did have some missing values in column 5. So this tells you that that happened and that it named that column X5. So if we look at this, we can see, once again, Tibble, same sort of thing, but it now added an extra column there. And that is because I intentionally went in and inserted a space into one of the cells, just to show you how that gets treated. If we had used the trim white space, it would not do that. So once again, we can do the same sort of thing. We can look at the head of that land crab's tab. Displays the first 6 rows of that, and we can look at the structure of that. And because we know that there is that land crab's tab 5, back to this here, is all characters. Because there's some missing thing, there's no information really in there, we can do land crabs tab revised would be land crabs tab, and we can provide the index and say we want all rows, but we want to cut column 5. And then if we look at this now, we see that we now dropped out that 5th column that was causing us errors. Another kind of data frame that you will also see is Excel. And there's a lot of packages out there that are trying to deal with Excel files. But if you are on a Mac or on Linux, a lot of times you will run into all sorts of problems with the drivers are not loaded. It can be a really big pain. There is a package library that's also part of the tidyverse that is read Excel. That when you need to load in, it doesn't automatically load when you load tidyverse. And there is a function read_Excel in there. And here's a little description of it. Once again, you've run the function. You can provide it the path that you want it, that you're drawing the Excel file from. You can select sheets, so you can have different sheet numbers being brought in. You can have some rows skipped, column names, all of those kind of things. That were the similar as the read CSV. The nice thing about this read Excel is that it has its own drivers, I think Java drivers, within this package, so you don't need to have extra drivers loaded or any of those kind of things. It all comes installed with read.excel. So you can kind of see here, we'll do the same thing. We're going to now bring in the XLS file. And it's the same data that we had. We can also specify we wanted sheet 2. You can bring that data in. And you notice here that I had missing data put in there. This doesn't automatically recognize NAs as missing data. So you can see that when we brought this in, there was NAs in there, but it recognized it as character data rather than missing data. We can address that with this read Excel. One path. By saying NA is equal to NA. So now when we run this, you can see that we now have this back as numeric data with NAs recognized as missing data there. So that works with both XLS and XLSX. It's a pretty good package. There's a couple other examples. I think we're getting long on time here. Yeah. There are a couple other packages also part of the tidyverse that bring in SAS, SPS, and Stata data. That is called it's the Haven package, and I'll provide examples up on the GitHub page for those if you want to use those. I did want to try to show you one other thing that you can do that's pretty handy here before we close out, and that you can combine the rcurl package, which allows you to read things off the web onto your computer. So you can tie directly into GitHub rather than going to what we did at the beginning, downloading that file. You can go and use rcurl to get the URL, get the data, and not have to download it, load it all. You can read it right from GitHub. So I'll show you that quick. That is in the library rcurl. Oops. So if you need to, you do run install packages rcurl, and that will download the most recent one. You can run that. So then what we do is that we can go to let me get it up here. So we go back to our GitHub page. We can go into data. So if we wanted to load this CSV directly from GitHub, we can click on it, and then it brings up this data here. You need to take the raw format, so you click raw, and then just copy this link. You can then run embed this. We can go land crabs. Git, and we can go read curl, because that was a CSV that we wanted, or read CSV, I mean. And then you go use the rcurl function, get URL, and then we will put this, oh, we need quotes. Paste that inside here. We can run this. See, it took a second, but now we just read that straight from the GitHub page right into our. This is really helpful when you're exploring packages or looking at what some other people might have up on GitHub. It makes it really nice. In the instructions that I'll also put up on the OFWIM page on some of the data input, I'll also show you how to use, there's another way to get our data sets from GitHub too. That's a little bit different than this method. So we went a little bit long today. Apologize going over a bit. We covered a lot. But if you want to go back in, I'll get these pages up today on the OFWIM site if anyone wants to explore and stuff in any more detail. What I plan on in a couple of weeks here is that we will work on manipulating data and crunching the data, and then going into some publication graphics. Three more of the it really make things a lot easier than what you've traditionally had to do in R. Did anyone have any last-minute questions? We good? All right. Well, thanks a lot. Glad to have you guys all watching here. I hope this is helping. Thanks.
Thanks, everybody. We'll see you in a couple of weeks at Bonka. This recording will be up in a couple of days on the OFWIM website.